started? Okay, so welcome to the second session. So let's have a quick review of what we talked about last week. And for Jerome who missed last week, you didn't miss that much. We're just getting started. So last week we talked about the basic logic operators. There was the constants, what we call logical constants, true and false. They never changed. They are called logical constants. We talked about a few logical operators. This is what we call a unary operator. So unary means it applies to only one logical statement. That's not. Okay, so you say not something. And then we have some binary operators. It means you apply the operator to two statements, so A and B. Right? You can have A or B. We also talked about A implies B. And obviously, implication is a bit more confusing than the other ones. So these are all still very basic stuff. And I think for final year undergrad, probably way too easy, but we've got to start from the basics. All right, so this time we're going to give more examples to help you understand their semantics a bit better. Okay, so we'll look at some examples, and then from those examples, we'll build up the so-called truth tables. So that was the matrix-ish thing that you talked about last time. So let's have a look at and. Let's say yeah, or maybe let's just go from the order. So the first one was not. There's nothing much we can talk about true and false. True is just true, false is just false, all right? So not is really simple. Okay, it's really simple. So let's have a statement. Let's say statement is Z is a student. Okay, so the statement goes Z is a student. Okay, and we want to apply the not to the statement. So not Z is a student, and that just means Z is not a student. Okay, and the truth value of this not statement depends on whatever statement that's applied there. So it depends on the truth value of Z is a student, and I'm not a student, so that's false. Therefore, the not statement is true. Right? So that is a true statement. Okay, that's a true statement. And on the other hand, if you have a not, Z is a stuff. Okay, because I am a stuff, then the negation of that statement is false. All right, so that's straightforward. So that's false. And not is really simple. And another simple one is and. Okay, it's and. So let's begin. Well, obviously, now that we've got and that connects two statements, we can have, depending on the truth value of each statement, we can have 4 possible outcomes. Okay, so you can go something and something. And on the left-hand side, we can have Z is a student. On the right-hand side, we can have Tessa is a staff. Okay. So the left-hand side is false. Right-hand side is also false. Therefore, the and statement is false. Okay, so that's false. But what about Z is a stuff and Tessa is also a stuff? What about this one? It still be false. All right. because left-hand side is true, right-hand side is false. Therefore, the AND statement is still false. Okay. Next case, Z is student and Tessa is a student. Okay, so I would count PhD student as a student. Therefore, the right-hand side is true, left-hand side is false. Therefore, the AND statement is still false. Okay. And last case, Z is staff and Tessa is a student. Okay, and now the left-hand side is true, right-hand side is true, the AND statement is true. Okay, that's the only case when the AND statement is true. And we can build truth tables based on those examples. All right, so, well, I guess we can begin with the truth table for not. So the way we draw a truth table is we've got a few rows, a few columns. The first column is, let's call it a variable. Actually, maybe I'll just use, let's say the statement is A. So this statement, let's call it A. All right. Need one more. And then the not statement is not A. So if A is false, okay, A is false, it's 0. 0 means false. A is false, not A is true. Okay, so that's 1. And if A is true, we have a 1 here, then not A is false. Not, it's called negation. It negates the result of the original statement. Because there's another name for it, it's called negation. All right, so and is another name for and, it's called conjunction. Okay, and the way we can draw a truth table, we'll need a few more columns. One more actually. We need the left part, we need the right part, and we need A and B. Okay, so first case, if A is false and B is false, A and B is false. If A is false and B is true, A and B is still false. Okay, these are quite basic. I think it's probably covered in your high school.
That's the first year.
First year?
Yeah.
All right, so the third case, A is true and B is false. A and B is still false. And it's only when both A and B are true, A and B is true. All right, so that's very straightforward. So no questions here. Okay, now we've got not and then this or. So or is a little bit strange. Okay, because here we're talking about inclusive or, not exclusive or. Okay, so let's take the same statements. Z is student or Tessa is a staff. So is this or statement true or false? The left-hand side is false, right-hand side is false, and false or false, you get false. All right, that's wrong. That's false. Now, Z is a staff or Tessa is a staff. Now, what about this one? So left-hand side is true, right-hand side is false. True or false, you get true. Okay. And third one, Z is a student or Tessa is a student. What about this one? False or true, you get true. And if I say Z is a staff or Tessa is a student, so true or true, obviously you get true. Okay, so how do we draw the truth table here? A, B, we have A or B. Okay, if both are false, then you have false. And if one of them is true, you get true. And if both of them are true, then it's still true. Okay, so if you look at the truth tables, when we are having a conjunction of two statements, the conjunction is only true when both statements are true. Otherwise, it's false. Whereas when you have an or, which is also called a disjunction statement, when you have a disjunction, the result is only false when both statements are false. Otherwise, it's true. Okay. So a disjunction is only false when both disjuncts are false. Otherwise, it's true. Okay. So that is or. Now here comes, I think, the tricky part. The tricky part is implication. So we don't actually use implication that much when we do programming. Right? So in your programming language, you do and, you do or, you do not. So those three are basic, logic operators you do in everyday programming. You don't do implication as much. So let's have a look at the 4 cases. Z is a student, implies Tessa is a staff. It reads very funny. It may not even read, something that makes sense. Like it doesn't make a lot of sense. But the left, from a logical language point of view, left-hand side is a statement, right-hand side is a statement. So we can connect it with an implication operator, right? So the left-hand side is false. The right-hand side is still false. Then what's the truth value of the implication? What's the truth value of the implication? Now, so you can think of implication as a statement. If the left-hand side is true, then the right-hand side must be true. Okay, but if the left-hand side is false, then can be anything, and now the left-hand side is indeed false. So the implication is called it's vacuously true. Okay, so that implication is true. Right. You can also think of an implication as the left-hand side is your assumption, the right-hand side is your conclusion, right? And if your assumption is false, you can conclude anything. You can conclude anything you like, and your reasoning is always true, okay? Because you assumed something wrong.
Like there's always one truth, but there can be many falses. So like the criteria for it to be false is a lower bar. That whatever it lands, or is it still a one-to-one relationship?
It's still a one-to-one relationship, so not quite like that. I mean, this is just the definition of implication in the logic point of view. So in your natural language, when you speak and when you write, implication may mean something else. Right? So this is just how the semantics of implication is defined. Okay, so if the left-hand side is false, the implication is automatically true. Right? May not make any sense at all, but it's true. Right. So second example, if Z is stuff, implies Tesla is a stuff. Okay, so now the left-hand side is true. The right-hand side is false. What do you get here? It's false, right? So implication says if the left-hand side is true, then the right-hand side must also be true. All right, so now we have the left-hand side is true, but the right-hand side is false, so it's false. What about the third case? So this student again implies Tesla is a student. So left-hand side is false, right-hand side is true. What do you get? So false. Again, the rule we apply is if the left-hand side is true, then it's true. Right? If the left-hand side is false, then it's true. Right? So that one is still true. If your assumption is false, then your implication reasoning is true. Right? So lessons learned is, you don't want to assume something wrong. Otherwise, well, your reasoning is true, but it doesn't make a lot of sense. Right? It's not useful, not really a useful reasoning. That's why it's vacuously true. Okay, so when you have an implication, if the left-hand side is false, then the implication is true. That's the rule we apply here. The last one is stuff implies Tesla is a student. So the left-hand side is true and the right-hand side is also true. Therefore, it is true. Okay. So implication. If implication only cares about one thing, if the left-hand side is true, then the right-hand side must be true. Right? So the only case the implication is false is when the left-hand side is true and the right-hand side is false. That's only case when it's false. In all other cases, it's true. Okay, so if we want to draw a truth table, A, B, A implies B. Okay. Now, if both are false, you get, what do you get? A is false, B is false. You get true, because the left-hand side is false. If the left-hand side is false, then it's true. If A is false, B is true, then obviously it's still true, because the left-hand side is still false. Okay. If A is true, but B is false, then it's false. All right, so that's the second line, the second case we got there. That's only case when the implication is false. Okay. And if left-hand side is true and right-hand side is true, then it's true. Okay, so implication. The only case when it's false is when you assume something that is true, but you derive something that is false. That's the only case when the implication is false. In all other cases, it's true. Okay, so in all other cases, it's true. At the end of last session, we had this little thing here. We said A implies B is actually equivalent to not A or B. Okay, it's equivalent to not A or B. And we can actually prove it using truth table. So we can we know the truth value of the truth tables for not. We know the truth tables for or. So we can build up truth tables for more complicated form, right? So let's extend this truth table a little bit. All right, let's extend that a little bit. So let's have a not. All right, so what we want to have eventually is not A or B. Okay? Actually, we don't need to extend it that long. So this is, right, so that's what we need. Let me cut this off. And what we have here is an extended truth table. So what about this column of not A? Right, so obviously it's computed based on the value of A. So if A is 0, then not A is the 1. Okay. And second row A is still 0, and not A is still 1. Right? It negates A. If A is a 1, then not A is a 0. Okay. And if the last row is the same, A is 1, then not A is 0. Okay. Now, we need to look at the last column, so not A or B. Right. So the left-hand side is a 1, and the right-hand side is a 0. What you get is true, right? You get 1. And second row is the same. If one of them is 1, then you get 1. Right? And that's basically what you have here. If one of them is 1, then you get 1. If both are 0, then you get 0. That's the semantics for OR. Okay. Now, what about the third row? So not A is 0, B is 0. What do you get? You get 0. Okay. So that's 0. And then the last row, not A is 0, but B is 1. 0 or 1, you get 1. Okay. 0, 1, you get 1. Now, what do you observe here? What you observe here is that in all the cases, so one row is a case, right? So in all the cases, the truth value of A implies B is exactly the same as the truth value of not A or B. Okay, and that's why we say A implies B is equivalent to not A or B. Okay, so from a logic point of view, if you think the semantics of implications is a bit strange, right? It's sometimes counterintuitive. You just convert that into not A or B. That's how it's computed, right? And that applies, when you do programming as well. So when you do programming, if you want to write implication, but your programming language doesn't have that symbol for implication, what do? Well, you do not, and you do or. This is how you do it in a programming language. All right, so that statement is the same as A implies B. Okay, that's how you want to do it if you're doing programming. So truth tables are very useful tools. Okay, very useful tools. And because A implies B is equivalent to not A or B, oftentimes, when we define the syntax of a logic, we would just be, restricted to not and or, and then we say implication is defined by the previous operators. Okay, it's defined by not and or. So we call that derived operators. So basically, the idea is you can have a core set of operators, and then from there you can derive other operators. Right, and implication is one of them. Implication is defined by not and or. And we can have a few more defined derived operators. And some of them are really useful in, let's say, computer circuit design, as well as cryptography. So we've talked about implication. Or we talked about implication. And the next one we can talk about is, it's called exclusive OR. Right, so this this OR up here is inclusive OR, and obviously we can also have exclusive OR. So it's written as XOR, and if you've done some algebra, or if you do anything about circuit design, this is one of the basic logical gates, right? And there's a symbol for it. Usually it's written as a circle with a plus in it. Okay, exclusive OR. Now, can you sort of guess how can we define exclusive OR using the existing logical operators we've got? Right, so if we want to say A, oops, A, oh, by the way, I think people usually pronounce that as XOR, right? So A XOR B. What is A XOR B? How do we define this operator using the existing ones we've got?
B, like not A or B.
So being exclusive, that means either A is true or B is true, but not both. Cannot be both. All right. So that means you've got two cases. You've got two cases. The first case is A is true, but B is not true. Correct? So how do we express that in our logical language? A is true and B is not true. Right? A and not B. A is true and B is false. All right? And being exclusive, or two cases. The second case is A is false and B is true, and they are connected by OR. That's the exclusive OR. All right, so either A is true and B is false, or A is false and B is true. Okay. So that's how XOR is defined using the existing logical operators we've got. Okay. Now, I don't think we need any examples like that, but we can have the truth table right there. So what would be a truth table for A XOR B? Now, if A is false and B is false, then you get false. So you can compute that from this formula here. If A is false, that's false. False in anything is false. So the left-hand side is false. Okay. And if B is false, false in anything is false. So the right-hand side is false. And for and or if the left-hand side is false and right-hand side is false, you get false. So that's how you can compute it step by step, if you wish. How about A is false and B is true? What about this case? A is false and B is true. So A is false, that's false. Then the left-hand side is guaranteed false. Right, so there's big zero here. But B is true, and A is false. Right, so if A is false, then not A is true. Right, and true, you get true. Right, so the right-hand side is true. Now, because they're connected by an OR, then the result is true. Okay, then the result is true. All right, so let's have a look at this. The third case. A is true, B is false. Okay, A is true and B is false. So that's true. B is false. Not B is true. Correct? And true, you get a true. And true or anything else is true. Therefore, here you get true. Okay. So last case, if both are true, what happens? So here, see here. Now B is true. If B is true, then not B is false. And false in anything is false. So you get a big 0 there. On the right-hand side, again, A is true. So not A is false. False in anything is false. You get a big false on the right-hand side. So false or false, you get false. Okay, that's what you get in the end. Now, if you look at the truth table for XOR, you'll notice that's exactly exclusive OR. Right? So either A is true. So look at the cases, the middle two column and the middle two rows, where A or B is true. Right? That's when either A is true or B is true, but not both. Right? When A and B are both true, you get a 0. When A and B are both false, you still get a 0. Right? That's exactly what we mean by exclusive OR. Okay. Now, the other way, if you want to memorize this, is for A or B, if their truth values are the same, then you get a 0. If they're different, then you get a 1. Okay. So that's a useful derived logical operator. Useful derived logical operator.
Can anything be derived from not and or? Is that kind of are they like base?
So that's a very good question. It depends on what do you mean by anything. In the context, in the scope of propositional logic, which is what we're talking about today, then yes. So all the other logical operators can be derived by not, and or. And in fact, so people have. So it's actually a very important question, right? So people have developed the minimal set of things you need to derive everything else in terms of the language point of view. So the minimal thing you need is basically just you need one of the logical constants. Right? You need one of the logical constants, and then you need and then you only need one of the logical operators, and you can derive everything else. So essentially the minimal set of things you need is actually really small. It's a very small set. So I think the core set is it's only false. It's only false and implication. So these are the only two things you need, and then you can derive everything else. Okay. So so this is going a little bit different than what I plan to do, but being a reading group, there's nothing really planned, right? So let's continue this because this is probably some topic I probably would talk about 2 or 3 weeks later, but that's okay, right? I mean, we're a reading group. So if we only look at force and implication, how do we define let's say not? How do we define not? Right, so what is not A? If you only have false and implication, not A means simply A implies false. Okay, if A implies false, then A is not true. Right, so they are equivalent. They're equivalent. I haven't been drawing this symbol about equivalent because that's another thing I wanted to derive. All right. So technically, there's a symbol called equivalence, but we'll talk about that in a second. So not A is A implies false. And what about true? All right. So true, what is true? True is the opposite of false. In other words, true is not false, basically. It's not false. And we know how to say not. Not is something implies false. Okay, so true is essentially false implies false. That's true. Okay. Now what is A or B? Right. This one's a bit complex, right? So so you know that there's a relation between or and implication. Right? You just need to reverse engineer that relation, and then you get the definition for or, and then you get definition for and, but eventually you can define everything else. So that's the idea. I'm not going to expand that today, but that's the idea. So not and implies, they're actually the minimal things you need to define everything else. But for today, there is still something else that I wanted to derive from the existing logical operators, and that's exactly the equivalence relation that we've been talking about the whole time, but I just haven't defined it yet. So I usually write the 3 lines to mean the equivalent. There are a few different ways to write it. So it's called equivalence. Okay, it's called equivalence. And sometimes we write 3 bars. Sometimes we write a left and right arrow combined. Okay. So based on the second symbol, you can roughly guess how to derive it from the existing logical operators. So A, what we pronounce is A is equal to B, right? What does it mean for A to be equal to B? Well, this one is defined as A implies B and B implies A. So you see the implication goes both ways, right? That is equivalence. A implies B and B implies A, then they're equivalent. Okay, that's called equivalence. I think those are the useful logical operators we're gonna have. Obviously, there are more, but those are the useful ones. Okay. Now, speaking of equivalence, there's another word that is really similar, but it's different. Okay. Yeah, from what James Franco. Same but different, but they're different. Okay, they're really different in this case. All right, so the other word is called equality. Okay. So I guess from a language point of view, can you explain to me, what is equivalence and what is equality? Is there any difference between the two?
Suggest that like they are identically the same, whereas equality could be different but of equal standing. Yeah.
I don't know how it's defined in the language, but from a logic point of view, or this is not just logic point of view, this is actually from algebra. Okay. So from mathematics point of view, it's actually the other way around of what you just said. Okay, so it's the other way around of what you just said. Yeah, you could be right. You could be right if you're talking about English, but in algebra and mathematics, equivalence equivalence essentially means you're talking about two things that are sort of equal in some certain way, but they could be different things. That's equivalence. Whereas equality essentially means they are the same thing. Okay, so if you actually have my book somewhere at the beginning, so equivalence is defined as three important properties. It's reflexive, it's symmetric, and it's transitive. Okay, so actually I may write that somewhere down here. All right. So we're talking about equality here, equivalence here. Equivalence has three nice properties. First one is called reflexive. Okay, what is reflexive? It means it reflects to something reflects to itself. It means reflexive. And when we're talking about a binary relation, reflexive means A, anything, take an example, just A, is related to itself. Okay. So A is equal to itself. Make sense? Symmetric. What is symmetric? It means if A is equal to B, A is equal to B, then what do we get? We get that B is equal to A. The relation is symmetric. Okay. So if A is equal to B, then B is equal to A. And then the third one is transitive. Okay, so transitive means if A is equal to B and B is equal to C, then what you derive is A is equal to C. Okay, because the relation transits from A to C through B. It's transitivity. Okay, so any relation that satisfies these three is an equivalence relation. Okay. Any relation that satisfies the three properties and equivalence is an equivalence relation. So we can take an example. We can take an example of an equivalence relation. Let's say somebody and somebody else have the same birthday. Okay, have the same birthday. And I claim that this relation is, so it's a binary relation because there are two blanks in this statement. It's a binary relation. And I claim that it's an equivalence relation. Why? Because it satisfies the three properties. Okay, so first let's look at reflexivity. Okay, that means A has the same birthday as himself. Now, obviously that's true. Right? You have the same birthday as yourself. Now, I also claim that this relation is symmetric. So if I and Tessa have the same birthday, then Tessa and I have the same birthday. Symmetric. All right, and then this relation is also transitive. So if A and B have the same birthday, B and C have the same birthday, then we can deduce that A and C have the same birthday. Okay, so reflexive, symmetric, and transitive. Therefore, this binary statement is an equivalence relation.
C in the last one.
Just another person, essentially. Right? Just any other person.
Calculate within that statement too.
Yeah. So you can take any examples. any entities. All right, but obviously it's not an equality relation. So equality relation is actually equivalence plus something else. All right, so the algebraic definition of make it too small, of equality is actually defined as equivalence plus something else. So essentially it satisfies all the three, and it satisfies another one called antisymmetry. It sounds a bit funny because it satisfies symmetry and also antisymmetry at the same time.
Really had a field day of dictionary on this.
They should words or anything.
Honestly.
So what is antisymmetry? Antisymmetry means if A and B satisfy this relation, this equality relation, okay? Maybe I'll just write the symbol, the usual symbol we use for equality. That's the equal sign. All right, that's the equal sign. Then A and B designate the same object, essentially. That's what's on top of equivalence. So this have the same birthday relation. It's not an equality relation. It's just because, you know, I and Tessa have the same birthday doesn't mean we're the same person. Right? So equivalence is not an equality relation. May not be an equality relation. Right? So there's a slight difference there. It's a slight difference. All right. So it's the next thing on our agenda. I think the next thing is, so we talked about equality, we talked about equivalence. Maybe we can, and we also talked about truth tables. So that's a lot of things we covered. All right, so I think we have 7 minutes. 7 minutes, and I recall last time we actually ran ChatGPT and it gave us some funny answer. So today we're going to look at that. And now that we've got some understanding of logical formulae and their semantics, so let's have a look. Took a screenshot. Oops, that's not this one. That's this one here. That's a screenshot. So on the top is a question we asked ChatGPT. Right. The question is, A implies B. Not C implies not B. And A is true. Now the question is, what's the truth value of C? What's the truth value of C? And can we say C is true? And ChatGPT said, no, it's not necessarily true. And then it gives you a bunch of explanations, right? It gives you a bunch of explanations. Now, I'm not going to read into details of what it explains, because, you know, once you try to read it, you may get confused and you may actually think, oh, it makes sense. It makes sense. But let's look at the question. Let's look at the question. So the question says A implies B. All right, so what we know is we know A implies B. Okay, that's what we know. And what's the second thing we know? Second thing we know is not C implies not B. Okay. So not C implies not B. All right. And the third one is A is true. Okay. Third one is A is true. Now the question is, what about C? What about C? And from a logic point of view, it's really, really simple. Okay. So what is A implies B? A implies B says if A is true, then B is true. right? And we know that A is true. We know that A is true. So what can we deduce from here? What can we deduce from? All right, so let's number them 1, 2, 3. So we can say from 1 and 3, we can deduce that B is also true. Okay, we know that A is true. We know A implies B. Therefore, B must be true. That's what implication means. Okay, so if you are not convinced, we can look at the truth table that we drew earlier today. A implies B. Okay, so we know that A implies B is true. That means it's either the first row or the second row or the last row, because A implies B is true. And we know that A is true, so that's this one or that one. So combining that, we know that must be the last, it must be the last row. Right, so what do we have in the last row? We have that B is true. Right. So we've established that B is true. And from B is true, what else can we derive? Right, so this interesting thing is not C implies not B. All right, so I'm going to use a technique called proof by contradiction. Well, wait, I'm going to use another one. I'm going to do proof by assuming the wrong assumption. Okay, so we have not C implies not B. Now, I'm going to assume that C is false. Okay, I'm going to assume that C is false and see what happens. Right, see what happens. So if C is false, then what is not C? Not C is true. Okay. Then not C is true. And if not C is true, what can we derive? We have an implication there. If not C is true, then using number 2, we have that not B is true. That's implication. If the left-hand side is true, then the right-hand side must be also true. So if not C is true, then not B is true. And what do we derive from here? If not B is true, then B is false. Then B is false. Okay. And then we have a contradiction. What's a contradiction? Well, we just derived that B must be true. Right? But B is true. Therefore, we have a contradiction. Right? We have a contradiction. And why do we have the contradiction? The reason why we have the contradiction is because we assumed something that is incorrect. So the only problem in this reasoning is this guy here. Right? And what can we conclude? This whole trace of reasoning concludes C cannot be false. Right? C can't be false. If C is false, we derive contradiction. Therefore, C is true. Okay, so the answer to this question is C is necessarily true. It must be true. Okay, so that is the logical reasoning here. Now, obviously, ChatGPT is wrong. Okay. And this is actually very elementary logical reasoning. So
GPT's got some studying to do.
It's got some studying to do. ChatGPT needs at least our session 1 and 2. Yeah, so I think currently, I mean, technically speaking, ChatGPT is really good at, I mean, it has a huge knowledge base. And if you ask a question, it's really good at finding relevant information from its knowledge base. And it's really, really good at putting things together and making it read, reasonable. But it doesn't mean, it does logical things, right? So it could be putting together things that are, contradictory to each other, which is what happened here.
Any domain knowledge really.
Yeah.
But if you're right, if you look at an area, you don't know, probably stand, right? So
Yeah.
like just sort of the UX and something, but I think that's the thing
Yeah,
you said.
it doesn't.
Like those are the words, but not the context.
Yeah.
Okay. So covered that example, shown that ChatGPT is wrong in this case. So that's how we need to do today. I mean, that's 2 p.m.
Put gas and lighting into
Yeah.
but you get gas.
All right. So I guess we can stop the recording and thank you everybody for today's session.